I'm Luke Imhoff. I'm known across the internet as Chronic Death. I work at Dockyard. I created the IntelliJ Elixir plugin for JetBrains IDEs, such as RubyMine and IDEA. While working on IntelliJ Elixir, I've learned some weird and esoteric corners of Elixir OTP in the Beam, which I'd like to share with you today, and why you can never debug the code you run, but you can view the code the debugger is running. When debugging Elixir code, there are three classes of tools: print-based debugging using IO, pry-based debugging using iex.pry, and line-based debugging using graphical debuggers. There's also the entire category of tracing, but I'm not going to cover it in the talk today because other people cover it better, and I'm still not good at it. So show of hands, what does everyone use? Who does print-based debugging? Yeah, everyone does. What about pry? Anyone use pry? What about graphical debugging? Is anyone surprised they did not actually know there was graphical debuggers for Elixir? Yeah. Let's start with IO. For main developers, print debugging is the first and last resort for debugging. It is fast and usually only requires a single line change. All the printing functions you'll need are in the IO module. Using IO puts, we can either print statements just to prove execution is actually at that point in the code. Usually this is all caps and screaming because you're like, why is this not working? Boom and bang, all in caps, or boom is very important so that you actually see it. It doesn't work otherwise. If it's too short, it just doesn't work. But you can also inspect variables with inspect. If you're going to use inspect, you can use IO inspect, which will automatically inspect its first argument, and it has the label flag. A lot of people don't know that. Very useful. IO inspect also makes debugging pipelines easier, as IO inspect will return its first argument, so you can IO inspect between two lines in a pipeline, and you'll see both the output and the input for the next call. IO inspect does have some limitations, though. To limit the amount of data it prints, it limits the number of elements in a list, the number of characters in text, and it hides implementation detail fields for things that override the IO inspect protocol. Unfortunately, those fields can be super important. This can be things like the action in ecto, so like whether you're doing an insert or a build, which can screw up how other functions work in the ecosystem. By default, IO inspect limits text to 4 kilobytes, while for collections it is only 50 elements. In both cases, you can completely turn off the limits with Atom Infinity. Of course, you're just going to print a lot of text, and you're going to probably slow your code down doing that. The text types of binary and list normally infer what to print based on checking if all the elements are printable Unicode. You can force them to assume text and print non-printable characters as Unicode, /U escape codes, using as strings or as char lists, respectively. If you're having the opposite problem, where just a list of numbers is thinking they're ANSI codes and printing out as text, you can use the as binaries or as lists option to treat it as just like packets. All of the key structs in the Elixir ecosystem that we use, such as Ecto's change set or plug-con, have inspect protocol implementations to hide private implementation detail fields. So these are things that we're not supposed to depend on being there, but can be the source of our bugs. So to be able to see those private fields, we have to use structs false, which turns off the protocol for those structs so that we see them as raw maps. If you're using IO inspect, you're likely, as a person, going to want to visually scan quickly as almost like formatted JSON. So you're going to want to print it the same way that mixed format does. Even more so, you're going to want to have the indentation for each level and not do what mixed format sometimes does, where it puts a list start, a tuple start, and a map start all in one line. So to do that, you tell it that your terminal has a width of 0. And it just will do a new line whenever it can, because it's allowed to go past the terminal width, but to try to meet your demands as soon as possible. Here's all those options put together. All these options are documented in the io.inspect module, not the IO module. Great, we're printing everything out. We can quickly see all the information, but the bug disappears. We have a timing-related bug that disappears because of the time it takes to print everything out. This has happened to me. IO-inspect can be slow because it uses what's called an inspect algebra to figure out how to do the formatting. The inspect protocol works on strings and not IO data at the end, so you're going to have to allocate an entire userland buffer to print out those big strings, which means you have more copying than a normal IO puts using IO data as you'd have in an EX template. The printable checks also have to scan the entire text that is going to be printed, so you're going to scan the string or the list twice. You're going to scan it once to be, is this Unicode that I can print? And then you're going to print it again if that's true, but only after doing layout. So you have multiple passes when you're doing inspect. If you find yourself wanting to print the file and line number instead of having to look up what an env or what double underscore thing we can use to print out the file and line number, you can just use IO warn, which gives you a nice stack trace where you issue the warning. This also has the benefit of that it's big, bold, and red, so that if you have your normal output being black or maybe blue, if you have the ANSI color debugger, it'll be a different color, so it's easier to spot visually. You may also recognize that IO warn looks a lot like deprecation warnings because that's what was its original purpose. It does, though, if your redirecting logs have the thing that is going to standard error and not standard out, so make sure you're redirecting both, or you at least have standard error capture and aren't only redirecting standard out. Moving beyond printing with the IO module, the next step for most developers is IExpry. Pry allows you to stop where you call pry and look at the variables or evaluate code. So it's more interactive than the IO modules. IExpry is a macro, so you need to require IEX before calling IExpry. But instead of putting require IEX like you would at top of module for proper clean code practices for code that you're actually going to commit, put it all in one line and use semicolon. Semicolon is allowed in Elixir. We just don't do it a lot. So you can smush stuff together. Don't check in the code, or I will know about it, and I will find your PR and comment on it. If you are worried about checking this in, Credo does have a check to check that you don't check this sort of stuff in. IExpry has seen progressive improvements in Elixir 1.5 and 1.6. Prior to 1.5, adding new breakpoints required editing the code. But 1.5 added functions for adding, listing, and removing breakpoints dynamically when you're already stopped. The stops argument, not a lot of people know about, is you can have a breakpoint hit more than once, so you don't get that prompt every time of, do you want to stop here? Do you want to stop here? Do you want to stop here? It'll just take the first prompt and allow you to hit that many more times, so you don't have to keep getting prompted, which can help in some timing and race condition situations. If you want to list all the breakpoints, you can do that with breaks, and that breaks will actually keep track of how many stops you have left, so you can see that. 1.6 added the ability to narrow the break call to a specific pattern. So you can do a pattern for the module function arity, and that way if you have a multi-clause function, you can target it. Elixir 1.5 also added multiple things for when you're actually stopped at those breakpoints. So a lot of people, if they use pry, are probably used to respawn, but there's also continue. So respawn kills off that debugging shell, and you'll get the prompt again, while continue keeps your like, yes, I want to stop here, and keeps going. So it'll be good if you don't want that yes, no prompt again. Two of the added functions in 1.5 make it easier to know where you are. Where am I and open. Where am I adds console debugging niceties like you would see in GDB's text UI. So those are the location, such as the file and line number. This is relative to the current working directory when you launch the project, so you can usually copy this and open it in an editor. Below those lines are lines of context. This is actually tunable. IExpry has config options, so you could actually make this wider if 2 lines on either side isn't enough information for you. And then finally, there's a stack trace. But it's still an Elixir stack trace, which means tail call optimization has happened. So sometimes this isn't enough to debug your problem because you had tail optimized calls and they just disappeared, so you don't actually know what happened. If anyone isn't aware of this, they're too new to Elixir to have seen this problem, that if the last call in a function is another function call, and it doesn't take a return value and do something else, that stack frame just disappears because it kind of like it erases it at the C level. And so you're only going to see the things where they have to return in the middle of a function, which can make it very hard when all of a sudden code jumps from like XUnit to code that you did as a callback and you never see the interleaving like libraries you're using. While where am I shows the context of the breakpoint inline in the pry shell, the open command opens the breakpoint in an editor. But open takes pre-planning. So you either have to set the Elixir editor or the editor environment variable. You may already have editor set because a lot of command line tools like Git either have the option of using editor or Git editor. So if you set editor, it'll already be set up and it'll probably be set to like VI or Vim. So you might want to check that in case you get stuck in VI and you don't know what you're doing. And also, it can be super annoying, and this has been moved forward on a remote system where I did not have editor set up, and this failed, and it took a really long time to reproduce that bug. So check it if you think you're going to use open ahead of time. IXPry and any of the breakpoints added with break don't just slow down the code on our test, but actually block you from proceeding. So even though it's asking, do you want to stop here, that process is already stopped, asking you if you want to stop. So it's kind of like, yeah, you already stopped. But the thing is, this isn't a complete stop of the VM. The Control-C menu, when we do Control-C, that is actually breaking everything in the VM is frozen. But this is just freezing the one process that's called IXPry. So all your timeouts, all your remote calls to like HTTP, all that is happening in the background, and they all could be timing out while it's waiting for you to notice that the breakpoint finally got hit and ask you if you want to stop. So this obviously can lead to issues. If the breakpoint's code is in multiple tests, you can get flooded by requests to pry, and it can get quickly confusing about which pry shells you end up in. Each one of the prompts here looks the same, and it's difficult to tell which pry is prompting. Turning on --trace so the test names are printed can help, but because the printer recolors the test name whether it passed or not, you actually get interleaving lines and double lines in different ANSI colors. So that can be confusing. Trace does have the benefit, though, is it turns off the 60-second default timeout in XUnit also. It is pretty much the only way to do that from the command line. So if you need to stop the 1-minute timeout from killing your pry session, use trace also. If you have too many hits for a breakpoint, your first recourse is, of course, to run that code less. When debugging tests, this means running just that one line. Be careful and don't do the line as the line in a describe block, though, because that now runs the entire describe block, which is a nice feature, but it wasn't always that way, so that's a change that has happened. If that doesn't work, though, and one test calls the breakpoint multiple times, you can use breakbang's pattern and guard support if you know the arguments to the problem, but you are triaging an issue, so you might not know those arguments. If that's the case, you're going to have to manually implement conditional breakpoints. To manually do conditional breakpoints, we need to set up an agent to hold the flag, toggle the flag around the call, and check if the flag is on at the point we're going to pry. In a setup block, we're going to call agent start link. We'll start with the breakpoint disabled and give the agent an arbitrary name so that we can access its state in both the trigger and breakpoint location. Given we have multiple call sites for the code on our test, we're going to toggle the breakpoint on and off by just taking a random guess about which one is the problem. Since the code on our test was the last call in the function, we'll need to add a variable to capture the result. I point this out because I totally forgot to do this, and then of course the function started to return OK, because that's what update returns. In the code under test, we can check the condition agent state and only pry when it's true. Sometimes, though, such as in recursive code, we can't turn the breakpoint on off around a specific call, but instead we want the breakpoint to flip on after a certain number of preliminary calls. For that setup, instead of using a Boolean flag, we can use an integer to count the hits. This is opposite from the stop argument to break, because the stop is I'm going to stop from 0 to n calls. This is going to be ignore the first n calls. When using a count condition, the trigger and the breakpoint become the same place. So we'll use agent get and update instead of a separate agent.update and agent.get, so we don't have any race conditions about accessing the agent state. Here we're going to break after at least 3 hits. But of course, you're free to do any truthy condition if you know it's exactly the third call that's being screwed up. Using an agent for condition also works with print debugging. Anything you want to do debugging-wise manually, you can nest inside of this check. So far, most of the examples have shown explicitly editing the code to add IXPry, which is obviously making the code you're debugging not the original code. But even using IXBreak, you're targeting functions by module name and arity, which means it matches for all the clauses and not like a specific line when you're editing the code. IXBreak also doesn't get access to imports or aliases, while editing the code to add IXPry does. So what's going on? They're both creating breakpoints, but they're not exactly the same. break is calling ixpry gen server. The handle call in the gen server calls a function called fetch Elixir debug info with fa check. It's a very good name. That function gets the currently loaded module's debug info. This is the same debug info that Jose talked about in the keynote. This is the debug I chunk that he added. The backend module is going to take in the debug from the debug info v1, which is the only version currently in the ecosystem. There haven't been any multiple versions yet. No one screwed up yet. Go us. And we're going to read the nested data. The nested data in the backend is in the Elixir v1 format. Additionally, we haven't changed our debug format yet, which is good since it's only been out, like about a year. The format was created in Erlang OTP PR 1367 if anyone wants to look up what all this does, what this got us, what an improvement this was over the abstract code format that we used to have to do, because the abstract code format only had Erlang AST, even when it was for Elixir. ixpry instrument is called with the output of fetch Elixir debug info with fa check. Instrument is structured using the standard recursive tree updates. It's a complicated tree, though, so it's a bunch of function calls instead of a nice, simple put in or update in. So it's going to update the module by updating the function definitions in those, and then those function definitions are updated by updating the individual clauses. To get access to the binding in the pry shell, instrument clause leverages macro prewalk to find variables and fake a binding. It's called prewalk because if you ever had to do like tree descent algorithms in a computer science course, it's like whether you walk the children first, or you walk the left child first, or sibling, it's that sort of naming scheme. Most of the stuff in Elixir seems to use prewalk always, so it's probably your best choice if you have to do anything weird with macros. The binding is then passed to Elixir ixpry, so the instrumentation is doing the same thing that you're doing when you manually edit the code. The case statement around the ixpry, though, is implementing the stops counter, so that pry is only called when there are stops left. So internally, ixbreak is implementing conditional debugging, and so this ets call is equivalent to the agent get and update that you saw before, but of course, counting from 0 to n instead of n and above. The instrument definitions with ixpry calls are in map. We're telling the backend module that the map metadata includes the instrument clauses are still in the Elixir v1 format for debug info. But we want the backend to convert it to the Erlang version 1 format, which is called forms. The compile module can compile those forms back to a binary module. But before loading the new module, we need to purge the old module. The code module, most of the access isn't to like pure functions. It's actually accessing what is called the code server, which is how hot code reloading works. That code server is keeping track of the two versions when you do hot code reloading. And so this purge is saying, get rid of the currently loaded version. Finally, since there's not a copy in memory, we can load the binary as the old version. We're using beam so it thinks it's from the same file, even though it's not. And we're using module so it's registered under the same module name. It'd be nice, though, to see what the code looks like as normal unquote Elixir, so that we can understand what is actually being run by the debugger when binary is used. To do that, we're going to need to debug the debugger, which will get us into graphical debugging. In order to see what ixbreak is doing, we're going to move on to the next debugger inside of IntelliJ Elixir. IntelliJ Elixir is the Elixir plugin for JetBrains IDEs. At all these it works in. Works best in IntelliJ IDEA, though, because it allows you to actually use multiple languages. If you do it in RubyMind, your project is still RubyMind. You just happen to have a component of it that does Elixir. Also, IntelliJ Community Edition is free. RubyMind you're paying for, so you can get a free IDE. I learned about Elixir from a talk that Dave Thomas gave at Lone Star Ruby in June 2014. I really liked using RubyMind for Ruby development. I was impressed that it actually worked on a dynamic language like Ruby. And so during the talk, I started to see if there was an Elixir plugin for RubyMind. There wasn't, so in July 2014, I found a tutorial on writing custom plugins and thought, Elixir syntax looks like Ruby syntax. So it can't be that hard to make an Elixir plugin. It took a year to get the fully correct grammar, but that time led to testing and found bugs in the native Elixir grammar. Since that time, it's gathered many new features. For our purposes to debug IX debug, we're going to use the run configurations, the graphical debugger, the disassembly, and the beam chunk viewer. So here I'm going to demonstrate using it. I'm able to place a breakpoint inside of the pry module on the line where we'll be able to view the binary. Normally, I'd have to edit the code and rebuild all of Elixir, but this way I only have to do a dot graphically. I'm setting up a run configuration to run ix-s mix on a test that I'm going to call ix breakin. I'm setting the environment to test so that it loads correctly and compiles in the test environment. So we're stopped, and we can see the binary, the individual bytes inside of it. I'm going to run the evaluator and actually write that binary variable out to a file by running Elixir code while it's stopped. Because I gave it a .beam extension, I can then open that file back up and load it as if it was a normal module. But unfortunately, the debug eye is not set when it's instrumented, so we can't actually look at what the debugger is doing. Instead, we go to the actual bytecode, which is this. And there you can see the IX pry call. So what were we seeing on the last part? That is not bytecode, because bytecode is a machine language. It would just be a bunch of ones and zeros or a bunch of hex escape codes in a hex editor. So instead, that is beam assembly. Modules, be they Erlang, Elixir, or other beam languages, are compiled to .beam files. A beam file is composed of chunks. There's an ATU8 chunk for UTF-8 atoms. That's also a Jose Valim change so that we could put his name as a variable. Because there used to be just an atom chunk, and that was only ANSI. Actually, Latin 1 ANSI, so like the ANSI with like Icelandic characters from Europe. There's the debug I chunk, also from Jose. And then there's the lit T chunk for literals. And then finally, there's the code chunk for bytecode. The code chunk contains some headers that say how much space to pre-allocate, and the rest is all bytecode, here in orange. Opcodes are not encoded in a normal term-to-binary format, but a more compact form that is unique to bytecode. You could read the raw bytes, but since each opcode's number of bytes is dynamic based on the actual type of the argument, it would not be easy to read ahead and be like, oh, I jump 4 bytes ahead and there's the next opcode. Doesn't work that way. The number of arguments is fixed, but their size and type is not. Instead of having to read the raw numbers, I created beam assembly language based on the beam disasm tool in OTP. The beam disasm tool, though, wasn't flexible enough. It has fixed rules about when to inline lookups in other chunks, such as atoms, literals, strings, and integers. But I wanted to be able to toggle back and forth with full inlining or no inlining so that I can understand what the beam is running or actually be able to read the damn thing. Oh, wait, maybe I'm not supposed to swear. Sorry, Jim. Finally, I made it easier to read than beam disasm by using named arguments instead of positional arguments, so that I didn't have to remember that the third argument for some thing is like the register or the jump that I'm going to go to. We're going to concentrate, though, on just the code that was added by the instrumentation. The first 5 instructions are the compiled version of the ets update counter in the instrumenter. The 6th instruction is a little weird, though. It's testing if the x0 register, which is the return from the last call, ets update counter, is not equal to -1, even though the Elixir code is testing for if it is -1. So why does the condition get inverted? Well, in general, all the bytecode instructions jump on failure, not on success. This actually does make sense if you think about if you were writing this in a high-level language or in C. Normally when you write an if, you think the if is going to happen, which means you don't actually want the if to jump. You want the jump to happen to go to the end, either the closing brace or the end in Ruby or Elixir. And so that's why you actually invert the condition when you go into assembly, so that the local path, so you have cache locality and you have the speed of you just load the next instruction. The ix.pry.pry call seems more complex than we'd expect from the code in actual Elixir, and it kind of looks like it's composing the binary in place. This is a side effect, though, of how Beam files efficiently store data. If I turn off the inlining for these lines, I'm going to turn off atoms, integers, and literals, and we can look kind of closer at how the actual code looks when it's run by the Beam VM. You can see that the binding is grabbing atom 21, which is the comma-separated relationships path. So that's the local variable that we want to actually show up in the pry shell. Binding is a map that is converted to a list with map to list, but because it happens inside the unquote, this is going to happen at compile time, which, remember, is actually at runtime because you're doing the break at runtime, so it's the compile time of the runtime. The list shows up in the bytecode instead of the map. The bytecode is mapping a 2-tuple with an atom key and puts that into a list, so it's actually making a keyword list. And so tuples are a little bit weird in bytecode in that you don't call one thing with all the arguments to make a tuple. You kind of pre-allocate, like, I'm going to make a tuple of size 2, and then the put calls fill in that tuple that you've allocated. So the Beam kind of has this state of just like, oh, a tuple is happening, please fill it in. I haven't actually tested how bad it screws up if you don't do that. Might be interesting. The unquote ops gets even better optimized, though. It just pulls from the lit T table entry 3. The compiler isn't able to use the literal for the binding, though, because it needs to put the value of the variable into that keyword list that is the binding. The Y registers, though, aren't actually registers. They're peaks into the stack. So Y0 is the top of the stack. The reason why it's called a Y register is the history of Beam. Just like the history of Erlang looks the way it does because it's based on Prolog, the Beam was originally based on a register VM called WAM, and that used Y for the stack, even though it was registers. And so it's still called Y here. We've seen that the IntelliJ debugger can debug other debuggers, but what else can it debug? Well, it can debug EX templates, which isn't easy because the Erlang AST doesn't keep track of files. It just keeps track of line numbers. The frames pane isn't a simple list of those frames like it would be in Where Am I or IL Warn. You can click and go down the frames to see the variables in those frames. This can be really useful for understanding the libraries we use, like Phoenix, JA Serializer, or Absinthe. Being able to step through the frames like this was when I was a Ruby developer. That's what I loved about RubyMine, because I quickly understood how libraries I was using actually worked and was able to debug them quickly. Unlike IXPry, IntelliJ Elixir has access to stepping commands. So not only can you put a breakpoint on a line, you can step to the next line after that. So we can step over, step into, step out. But because of the way Elixir code is generated, sometimes it just assigns the code to being on line 1. Because the code gets so optimized that it's just like, OK, it's at the beginning. So what happens here is instead of us jumping into the lines where the case statement is, so one of the clauses, it gets so optimized that it just says, this is generated code. Don't blame anything. It is only at the beginning of the file. But if you keep stepping, it works. It's OK. It doesn't break anything. Say we don't just want to view the variables, but we want to evaluate code. Well, as you already saw in the video, we can do that. But not just simple like single function calls like file write. Any of the macros also works. You can do cases, you can do withs. You can pretty much copy any code you have, and it'll work and do the translation for you. The full being able to expand and collapse variables also works in this view. The IntelliJ Elixir debugger, along with the Elixir language server, debugger support that works in VS Code, and the IntelliJ Erlang plugin, which all the debuggers are based on, and the debugger GUI that ships with OTP, which all of that is based on, use a module called int that ships with OTP. But what does int do? Like most names meant for use in the Erlang shell, it is overly terse. It means interpret or interpreter. So it interprets the bytecode we just saw, right? Because if the Beam's running the bytecode, you want to interpret the bytecode. You want to run the same. When you debug, you want to run the code that had the problem. Yeah, if only. Even though int allows you to debug in more places, you still cannot debug the code you run. Int is interpreting the Erlang AST. but we don't have Erlang AST. We have Elixir AST. So how is that possible? Well, the reason why it works is because part of that same thing from Jose was, since the abs chunk no longer exists, he said that if something requests the abs chunk, the backend is going to translate from debug to Erlang. So everyone has to support translating to Erlang, but Erlang can be picky about who it translates back to. So how does int get the beam to run Erlang AST instead of bytecode? Let's trace the path starting at int and I, which is how you say this module should be interpreted on every node I'm connected to with distributed Erlang. Int and I calls the much clearer name int mod. Int mod calls load. Load is where we start to get a hint of how the other modules are able to call into interpreted code. We're going to purge the current version as before. We're going to call this thing called ertz debug breakpoint false. So we found another debugger in the current debugger. The underscores in quotes, though, those aren't careless because this is Erlang. Those are atoms with weird names. So this is kind of like the don't care of match specs. So I'm going to assume that this is turning off all current breakpoints in this other debugger system for this module. We're then going to reload. We're going to tell the debug server, so the actual thing that does the interpreting, to load the code. But that means that we have both the normal code loaded and the debug code. So we still don't know why it picks the debug version that's being interpreted. But we turn the breakpoints back on, so maybe we should look at what the other debugger is doing. So how do we get from ertz debug breakpoint back to int? Well, the source in ertz debug URL isn't very helpful since it's a NIF, which means we have to go into C. So this is the C code for the NIF. If the flag is the atom true, then it's going to set a debug break. Ertz set debug break uses the constant ertz bpf debug, so breakpoint flag debug, which probably means there's other breakpoint flags besides debugging. Interesting. So you can look at that flag to find where the beam reads it back. Ertz bpf debug is converted to an idebug breakpoint operation in ertz generic breakpoint. We saw in earlier C code that the am prefix means that something is an atom, so this is going to call the breakpoint function in error handler. But what is error handler? Call error handler checks with the process info to find error handler. Oh, OK, so we're finally back to something we can call in Elixir. So let's call process info. So it looks like every process info dictionary has an error handler key, and it is set to error handler. So let's look for an error handler module, probably in Erlang since it's part of OTP. So if we look for it, we can figure out what the breakpoint does. In this case, it's going to call int eval. So we've made it back. We're back to int. Int eval calls debug eval. From the module name, it's probably the debug process because it's got debug at the end. And we know it has to be the debug process because the error handler is process specific. Interesting experiment to do is mess with error handler and see if you can implement a different type of debugger. The interpreter runs the interpretation in a meta process, which can be thought of as an interpreter for the specific process. This is a way to keep the process that we're trying to debug from not having messages about being debugged. We separate those concerns so that we don't, if we ever ask for what's the message queue for the process, we only get the real messages and not the ones related to debugging the process. It also allows that meta process to get messages from the graphical debugger that is separate from messages to the exact process. So to do line-based debugging in OTP from Elixir, we have to drop into Erlang by converting, go through OTP and C, manipulate the heart of ertz with the beam, where we leave a marker in the binary code that exists as an operation only in memory, never in the actual beam files, so that in the process that we actually care about debugging, it will read it back, go through C, but execute interpreted Erlang code, not our Elixir code, so that we can get notified that a line number that only exists in Elixir was hit, so that our graphical debugger can stop and highlight that line. That was a whirlwind dungeon crawl, and that's why I used the ghouls and ghost image. So let's review why you can't debug the code you run. For IO and IEX break, you can see you're modifying the source, so you're obviously not running the same code. But for all the ones where you don't edit the source, you edit the in-memory representation, so you're also editing the code. Execution is slowed by doing any of the debugging. Even the print-based debugging is slowing down because printing takes time. It can even be the case of whether you look at the code being printed can slow it down based on how your system is set up. Sometimes looking at log files will slow down like a make process or a build process. Just as a general note, any of the interpreted-based debuggers are going to run about 3 times as slow. So you really have to be able to be OK with taking that hit on the speed. So if every debugger alters the way that it runs in some way, how do you balance the benefits of triage and fixing bugs faster with your potential problems? I recommend using IntelliJ Elixir or any of the int-based debuggers if you're not sure how your code gets called by the libraries. If you want to understand the libraries or figure out why you're getting arguments you're not expecting, you want something where you can walk the stack frames back, and only the int-based debuggers can do that. But if you're hitting timeouts, go to IExpri. You'll be able to do Linebased if you edit the code, and otherwise you'll be able to do break and do clauses. But since that still slows you down with the prompt, then just switch to IO. And of course, if you can't print anything, then you're in real trouble because it's just too slow. So if you have any questions about this, you can email me or contact me on Twitter or ElixirLang Slack as Chronic Death. I'm the host of the Austin Elixir Meetup, which has its own channel, Austin, on the ElixirLang Slack, so you can contact me there. I have the notifications there, so I'll see it right away. If you're interested in working with me, as I said, I work at Dockyard, so you can hire us, or you can email me directly, and I'll get you connected with our sales department. If you're interested in using the debugger or the disassembler I demoed for IntelliJ Elixir, you can download IntelliJ Community Edition for free. The plugin install happens inside the IDE the same way it does with Atom or VS Code, so you just search for it and you'll get it. If you actually want to see it, though, it is available on GitHub. It is a mix of Elixir, Erlang, Java, and Kotlin. So if you want to see how to emulate the macro module in Elixir in Kotlin, it's in there. Finally, Dockyard as a company is holding a raffle of 2 hours of Chris McCord's time where he'll consult on your project. It's at our booth upstairs. Just drop your business card or write your name into the little Dockyard box, and we will draw names at 5 p.m. tomorrow. Thank you. OK, we got 3 minutes. Any questions?
Is there any sort of official documentation for Beam bytecode?
Oh, yes. So not official, but 2 great resources. So for Beam bytecode, there's a website called Beam Wisdom, if you Google for it. That one is how I figured out how to do the disassembler. There's also a new book that just became open source by, I can't remember his name, but his handle on GitHub is happy, but with an I instead of a Y. And it's called the Beam book, and it's now open source. And that goes into like all the internals, memory management, the bytecode. It is super great. And the reason why I couldn't get it published was because O'Reilly thought it would be too technical. And so they thought the user base would be too small. But like, if you care about this and how it works, read that. And if there's faults, it's now just a repo. We can PR it and make it better.
What was that first one again?
Beam Wisdom. So that one does the file format and like how binaries are packed and some memory layout stuff. It also has a bunch of explain it to me like I'm 5 things, so you can like read the overview and then try to digest it and then come back to the real version later. So that's nice too. Anyone else?
Is it possible to have the IntelliJ debugging stuff hooked up to like through a remote console to a production system?
Right now, I do not have that implemented because I make it launch because the way it works is it injects code with like require flags. There wouldn't be anything stopping it, though. I just have to implement it. In the 8.0 release, which was earlier this month, I did do it where if you add debugger as a dependency in a distillery release, it will launch the distillery release CLIs, and it can even work on releases then. So you don't have to do like a debug build or run with mix. You can run against a release.
OK, thanks.
OK, thanks.